appreciate it. So anyway, well, happy Friday, you guys. It's the end of week 3. It's I feel like the weeks are going by fairly quickly. We're about a third of the way through now, and yeah, we'll get through winter quarter. Today's lecture is on tidyr. It's on tidy data, and I recognize that there's kind of 2 different approaches or philosophies for teaching Stats 20. And so depending on how your who you had for your Stats 20 professor, you might have already seen some of this information, and others of you have not. So if you've already seen this, my apologies, but I hope it will serve as a good review, and you'll still find it useful. So so first of all, I want to introduce the tidyverse. The tidyverse is a kind of a set of packages, and a lot of my content for today is coming from this textbook, R for Data Science. It's an excellent textbook. You can read it for free. This link actually is broken now. I got to fix up the link in the slides here, but you can just type in R for Data Science, and it will take you to basically a web version of the textbook. You can read the textbook in your browser. If you want a print copy, you got to pay for it. You can buy it wherever you want. But you can get the just a version that you can read in your browser for you can read that for free. So anyway, the tidyverse describes itself as an opinionated collection of R packages designed for data science. And you're like, how can a collection of packages be opinionated? But they are all designed in such a way that it is expecting your data to follow a certain format, okay? And that format is the tidy format, okay? But there's a lot of packages that are very useful and very powerful for kind of data, working with data, cleaning data, manipulating data, things like that. And you're probably familiar with a lot of these things, such as ggplot, which is used for visualization. Tibbles, we're going to talk about Tibbles today, and tidyr. And then next week we'll look at dplyr. We've already seen reader as far as reading data into R. And then I might give like a quick glance over some of these things. Oh, we'll definitely cover stringer for regular expressions. So we'll get just a quick glance at per and maybe forecast as well. I don't know how much time we'll spend there, but let's talk about Tibbles. This is kind of the backbone of the tidyverse, and a Tibble is basically the same thing as a data frame. All right, so data frame is this rectangular 2-dimensional structure, but it allows for your columns to be of different types. And the Tibble is much like a data frame, except it's been updated. So the data frame is a data structure that was created with part of base R, and it had a lot of features that were nice at the time. But as the kind of data that we interact with these days has changed, the data frame has a few quirks that aren't as useful as before. So for example, one of the default behaviors of data frames is that all string data gets turned into a factor. Okay, and that was useful at the time where the only time you encountered string or character data was to kind of make categorical data. And if you have categorical data, then factors are very useful. But if you are working with, say, data from Twitter or something like that, that character string data should be treated as strings. And so in that case, turning them into factors is not useful. But anyway, so the Tibble is kind of a little refinement of the data frame. And you can create a Tibble much like the way you would create a data frame, in that you specify the name of the columns and then you put the data in there. And one thing about Tibbles is that when you print a Tibble, okay, so here I'm creating a Tibble with the columns A, B, C, D, and E, and the columns, each of the columns contain different types of data. Here, this is a time and date using the now function. It will be, 606, whatever. Yes, because it's a rectangle, the lengths of each of these things need to be the same length. So the length of each of these things is 1,000, 10 to the third power. 1e3 is 10 to the third power. So this will be, a column of integers. This is a column of type double, and this will be a column of characters, letters and things of that nature. Okay, and when you print a tibble, it will, by default, only print the first 10 rows, and it will only print the columns that fit on the screen. I don't know if you've had the experience where you type in the name of a data frame, and it's a big data frame, and then suddenly R just prints out like the whole data frame on your screen. It kind of fills up your entire console. You've got multiple columns, and one row goes across like several rows of things, and it's trying to print out like 999 of each of these things, and it says like printing stopped, 5,000 more rows and stuff, and you're just like, oh, I didn't mean to do that, right? And so the tibble by default will only give you the first 10 rows, okay? And there's ways to kind of ask for more rows from the tibble and things like that. And when you print this out, it also has a useful thing, which it tells you what type of data each of those columns contain. So here it says this is date time, this is a date, this is an integer, this is double, this is character, and that's useful. And then if you have a whole bunch of columns, it will automatically truncate it just to what fits on the screen, and it will say like with additional columns not shown and things like that. Okay, and so here it says with 990 more rows, because a lot of times when you print the name of a data frame, you only want to just see the first few rows just to kind of make sure you've got the get a feel of the data, and you're not actually trying to read through every single line. So that's a nice feature of the tibble. One thing that's important is that when you work with a tibble, especially when it comes to subsetting, there's a few things that are a little bit different, okay, than with the data frame. And so when you use the single square brackets on a tibble, it will always return a tibble. Even if you select only one column, it will always return a tibble. So here I've created a tibble, and this tibble has two columns, column X with the values 1, 2, 3, and column Y with the values 3, 2, 1. And here I want to select all the rows. I've got nothing selected here, but just one column. And so what it returns is it returns a tibble of one column, a 3 by 1 tibble. When you have data frames, if you select only one column, R will simplify it, and it will simplify it down to the atomic vector. And you can still do that with a tibble, but you just have to specify the option drop equals true. Okay, so you can specify drop equals true, and it will simplify down to that thing. But you can kind of think of it as, with a list, whenever you use single square brackets, it always preserves the list. And if you use double square brackets, it will extract the element. And similarly, tibbles are the same. Single square brackets will preserve it. Double square brackets will extract it. Here, just to contrast the data frame, when you use a single square bracket down to just one column, it will simplify it automatically. Okay. Whereas with the tibble, double square brackets will always extract. $sign notation will also extract, and both of these will come out with just the values, not the tibble. Is that good? Good with everybody here? As far as creating a tibble, you can create a tibble much the way you'd create a data frame. You specify the names of the columns and the contents. And again, the lengths of each of these things need to be the same. You can also take an existing data frame and just throw it inside the function tibble, and it will make it a tibble. Okay. And then in some cases, you want the person who's reading your code, you want that person to be able to know the values that went into the tibble. And so you can create a tibble row-wise, okay? So the general form is you create a tibble by column, you specify the column and the contents, but here you can create a tibble row-wise, and you use the function Tribble. I think that they were just being cute, trying to be cute there. And so T with a row, or R for row. So this is a tribble, but it's a tibble. And you just enter the data row-wise. And you specify your column names using this tilde here. And then you put in the contents here. And so we're saying in column A, we're having the character A, the value 1, the character B, the value 2, the character C, and the value 3, and so on and so forth. And this will recognize, okay, we're going to have a 3x2 tibble with characters A, B, C down this column and values 1, 2, 3 down this column as well. So that's so you can create this. It's very similar to creating a matrix, you know. So generally by R, when you create a matrix by R, it fills the columns column-wise. But sometimes I think in my code I've had examples where I said, you know, by row equals true, and that way you can kind of see the structure of the data that's going to go in there. Yeah, so for the tribble, you use the tilde, not the equal sign. It's a little bit strange. It's a little strange, I admit, but this is just how the tribble works. Okay, whereas normally when you specify the column name, you use the column name equals something, and this is kind of the traditional way of creating a tibble. But again, alternate version for creating a tibble via rows. You can do it like this.
Professor, I have a question.
Yeah, go ahead.
What's the point of, I mean, what's the difference between, well, maybe I missed this, but what is the difference between like the tibble and then the tribble part? Like, I mean.
They're both tibbles. Tribble is just in case you need to create a tibble, but you want to enter the data that goes into the tibble row-wise. So generally when you create a tibble or a data frame, you say, this is the name of the column, and this is kind of the values that go into that column. So here I'm just sampling five integers, and they're going to go into column A. Here's I'm just taking 5 random normal values, and they're going into column C. And this is kind of your traditional way of creating a data frame or a tibble. But if you want to kind of sometimes in your code you want the person reading it to understand the values that actually go into the thing and see it, and you can enter the data in kind of a visual form where it goes row-wise here.
Oh, okay, that makes sense.
Okay. All right, let me go ahead and give you your first quiz answer. First quiz answer is E as in elephant. E as in elephant. Your first quiz answer. All right, let's talk about pivoting data. Pivoting data is kind of an important function of this of the library tidyr, and that is to make data that is tidy. So there's kind of 3 rules as far as getting your data to be tidy, and that is that every column is a variable, every row is an observation, and every cell is a single value. Okay, and the converse, or I don't know what is, there's the inverse, the converse, and the contrapositive. I don't know, but anyway, I think the converse we need also needs to be true, right? Every variable has its own column, every observation has its own row, and every value has its own cell. Okay, and then that's going to make your data tidy. So here's an example of data that is tidy. We have some information about different hurricanes, I believe. Okay, and so we have the name of the storm, the wind speed, the air pressure, and the date this storm happened. Okay, so we have, I guess, Hurricane Alberto, wind speed of 110, pressure 1007, happened on August 12, 2000. Alex, wind speed 45, pressure 1009, and date July 30th, 1998. Okay. And so, you know, here are the column names, and we can see each column, I mean, each variable has its own column. Here's an example of data that we might not consider to be tidy. Okay. I mean, we do have data that's in a rectangle, and we've got rows and columns. But if you think about what are the variables being presented here, the variables being presented here are which country? So we have France, Germany, and the US. which columns, the columns are actually is another variable, which is what year is this information for? Was it the year 2011, 2012, 2013? And then the data here, these are the values, these are the counts of the cases. So this is just fictional imaginary data, and the cases are like the number of counts of some disease. Okay, so in France, in the year 2011, we had 7,000 cases. In 2012, we had 6,900 cases, et cetera, et cetera. And so if you look at the arrangement of the data, the variables, we have the country, the years is spread across columns, and then the values or the count of the cases is kind of in all of these, spread out across different columns here. And so we might want to try to rearrange this to be tidy data. Okay. All right, and here's another example of data that, one could argue this is already tidy data, but one could also make the argument that it's not. Okay, so we have a column for city. We have city, particle size, large and small, and the amount. Okay, and those could count as 3 variables. But one could say, what if I wanted to compare like the number of large particles to the number of small particles for each city? It's a little bit hard to do because the large particle amount and small particle amount are all in one column here. And so we could actually say, there's actually 3 variables. One variable is the city. One variable is the amount of large particles, and another variable is the amount of small particles. And so if you kind of say, well, how are the data arranged? The values, we've got the city in one column, okay? But the large particle amount is kind of on the odd rows, and the small particle amount is in the even rows. So this makes it a little bit tougher to work with because we've got 2 different variables that are being stored in one column. So so this slide is just to read in the data. The data is actually comes from this from a package in our studio, but just the raw data. We got the storms, the cases, and the pollution files. So I went ahead and brought in the storms data. Okay, and when your data is tidy, okay, you can easily create new columns using vector operations. So if I want to create a column where I take the wind pressure and divide by, the air pressure and divide by the wind speed, say 1007 divided by 110, I can just do that easily using a vectorized operation. I just do storms $pressure divided by storms $wind, and R will do this very quickly. Okay, and so if you need to take differences or something like that, you can easily do these vectorized operations. Okay, and so R makes it really nice and easy when to do different things like this if your data is already tidy. But if your data is not tidy, it's a lot harder to do these kinds of things. Okay, so let's take a look at our cases table and talk about how we could make this, say, tidy. Okay, so I won't see if you can think about this, and if you get the answer, you can unmute yourself, or you can put it in the chat. But let's say the variables that we want to keep track of are the country, the year in which we gathered these counts, and then the count themselves, right? So we got country, year, and count. And so if we rearrange our data to fit this, the question is, what will be the dimensions of the resulting data? How many columns will we have? How many rows will we have? Okay, so we'll have 3 columns. And yes, indeed, we will have 9 rows. Okay, 3 columns and 9 rows. So we're going to have 1 column for each variable, and our variables are country, year, and count. So we have 1 column for each variable. But then if we look at each of the observations, we have a total of 9 observations, and each one will have their own row. So if we take this and turn it into a 9x3 Tibble, this is the result that we're going to get. Okay, we're going to get all the countries kind of gathered here. And then these values, okay, are going to get gathered into one column here. Okay, so we got, you know, France, 7,000 cases, Germany in 2011, 5,800 cases, the US in 2011, 15,000 cases. Okay, so we're going to have a 9 by 3. Okay, and so the function that we use here is called pivot longer, right? And that's because we're taking our data, and the resulting table is going to be longer, right? Because we're taking values across multiple columns. Here, the values come across columns 2011, 2012, 2013, and we're effectively combining them or gathering them into one column. Okay, so we're going to be gathering these values across 3 columns down into one column, and so the resulting data is going to be longer. And so we call this pivot longer. Okay, and the arguments that get used in pivot longer are the names of the columns from which we are gathering values. Okay, so we're going to gather the values from 2011, 2012, 2013, and so we provide the name. So we say 2011 colon 2013. Okay, and these are column names, and it's you know, it's just coincidental that these are numbers, so we can kind of use this colon notation. But tidyr is actually smart enough to figure out kind of columns. So if the columns were January, February, March, you can just say January colon March, and it will just gather the columns in between those 2 names that you provide. Okay, and so the column names 2011, 2012, 2013, those are going to get entered into a new column, and those names go into the argument names2. All right, and so we're going to provide the name of the new column called year, and so the values 2011, 2012, and 2013 show up in this new column and we provided the name year. Whereas the values from that are spread out across, those are going to get combined into one column, and those values go to a new column called cases. Okay, and so we provide the name that we want to use for this column, and that column name is going to be called cases. Okay, this function used to be called gather in older versions of dplyr, but they renamed it to pivot longer. So sometimes if you look up like cheat sheets and stuff, it might have kind of the older function names, but it's the function is called pivot longer here. And so so this is the result. Okay, so we have France 2011 7,000, France 2012 6,900, France 2013 7,000, and indeed the data appears as it should. Okay, so I'm sorry, we had a question that said, where is country? So country appears here. You don't need to provide it in here because we left country unaltered, right? We don't need to put country anywhere inside the arguments because we are leaving this column country unaltered, and any column that we leave unaltered just kind of gets duplicated across here.
I have a question.
Yeah.
What's the difference between this data that you just converted, or this table that you just converted, compared to the pollution one, which you said that arguably it could be tidier?
Right. Well, I'll get to that at the end after we look at the pollution. Yeah. Okay. So just kind of again to reiterate the arguments here for pivot longer. You give it the name of the data that we're working with. Okay, and in this case, we're working with the cases table. The columns that you want to kind of gather, the columns from which the values are going to get gathered into one. And then this is just an arbitrary string. And here's another arbitrary string that are going to be the titles of the columns that they go into. Okay. What you provide to names to and values to is completely arbitrary. There's no meaning or no meaning other than what it means to you. And so instead of year and cases, I could have called it when it happened and how many. All right. These are not good names because they've got spaces and stuff, but it can handle that. And so the column when it happened appears here, and then the column how many appear here. And it's effectively the exact same data. It's just we've changed it to kind of a stranger name of when it happened and how many. So these are just arbitrary strings it's not that there's anything inherent to the meaning for year and cases here. They're just string values. All right, so here's a couple questions. What would happen if I run pivot longer, but the only columns I choose to pivot are the 2012 and 2013 columns? Okay, so what if I pivot only 2012 and 2013? What would the dimensions of the resulting table be? How many rows would I have? How many columns would I end up having? Okay, so the rows might be a little bit easier. How many rows would I end up having? Yeah, I would end up having 6 rows. And indeed, I would end up having 4 columns. Okay, so the values in 2012 and 2013, those get combined, okay, into this column here. And then, so we're going to get the column for year and the column for cases. And then the 2 columns I didn't touch, which were country and 2011, those just get duplicated for all the new rows that I've created. Okay, so I end up having 6 rows, and then we're going to end up having 4 columns: country, 2011, which got duplicated, and then year and cases. And then where cases, we've combined, you know, these 6 values into 1 column. Okay. If I pivot this, and what if I included country into the, as far as the columns that I'm going to pivot? What would happen there if I included country in the columns that I'm going to pivot? What would the resulting dimensions be? Okay, yeah. So, well, okay. So it says you can't pivot that, and that is initially true because country is character and the rest are doubles. Okay, so R is actually going to give me an error and says you can't combine character with type double. Okay, so it says you're not allowed to do that. Okay, but what if I insist and I say, you know what, I'm going to force everything into character, type character, right? Because I can just kind of convert all of these into character values, and I say, just do as I say, right? And if I do that, R will do it. Okay, so here I just kind of applied as.character to everything in the data frame. And then, and I pivot longer, and the result is going to be a 12 by 2. Okay, so all the columns, basically I combine all 4 columns into 1. And so it's going to treat not just these, not these 9 as values, but all 12 of these are going to get considered as values. And so we're going to have 12 rows. And we can see as far as the name goes, the column names, country, 2011, 2012, 2013, each show up in this column name. And then the values that it went are, you know, France, 7,000, 6,900, so on and so forth. Okay, this is a bad idea. This data has now been rendered useless because I've overzealously pivoted my data to be too long. But you know, tidyr is just doing what we asked it to do to kind of combine the values from these different columns into 1. All right, so here's the pollution table, okay? And we have, it's currently a 6 by 3 table, and we might want to take this column of values, 23, 14, 23 large, 14 small, 22 large, 16 small, 121 large, and 56 small. And we might want to take these values and we might want to spread them across different columns. We might want to create a column for large particles, and a column for small particles. And so if we wanted to do that, where we're going to take values in one column and spread them out, we call this operation pivoting wider. Okay. So if we perform this on the current data set here, the resulting data is going to end up being 3 by 3, okay? Because we're going to have a column for each city. I'm sorry, a row for each city, and then the columns will be the city, the large particle size, and the small particle size. Okay, so we're going to go from this 6 by 3 table into a 3 by 3 table. Okay, And doing something like this allows us to perform some vectorized operations. So for example, if we want to compare, what is the difference between the number of large particles and number of small particles, we can do that with a vectorized operation. We can just do large, column large minus column small, and it will perform the operation. Whereas it would be much harder to do something like that, to take the difference between large particles and small particles for each city, if all of the values appear in the same column. All right, and so the operation here is called pivot wider. Pivot wider. And so we take the table pollution, and we're going to say, you know what, take the names from the size column. The names for the column names are going to come from the size column. So we have a column called large and a column called small. And those names came from this table, or this column, size, large, small, large, small. Okay, so the names came from the size column. And then the values that go into here, these values, they came from the column amount, 23, 14, 22, 16. Those came from the column amount. And we took those values and we spread them across two columns, okay? We pivoted that data, that column of data, into something wider, right? So this operation is called pivot wider, okay? And again, older versions of tidyr had a different name for this. The different name was spread. Let me give you a second quiz answer. Second quiz answer for today is B. B as in bear. Or ball. B. Okay. So city here is just character data. Okay, city is character data, and it actually doesn't matter what city is. Well, I mean, okay, it kind of does, but here, all that matters is that we've got New York, London, London, Beijing, and it's going to take these and it's going to spread it out across here. Does the transformation make sense? Going from a 6x3 to a 3x3 here? Okay. All right. And so again, the arguments that go into the function are the name of the table that we're working with, the column that contains the names that will become the column names for your pivoted data, and then the column that contains the values that are going to appear in your pivoted data. So these have to be column names. So the column name was size and the column name was amount, okay, which is what we have here. All right, so pivot wider is sensitive to kind of spelling differences. So here, this is kind of the original data, my 6x3, and I've changed the top name from New York to NYC, right? So you might abbreviate New York City as NYC. And what if I run this table through the pivot wider operation? Okay, so we're going to say, let's take the size column and create new column names, large, small, large, small. Let's take the amount and put those into the values. So the question now is, how many rows will I end up having? How many columns will I end up having if I do this? Yeah, I would end up having 4 rows and 3 columns, indeed. Okay, we're going to have a row for NYC and a row for New York. Okay, and then London and Beijing will work fine. I've got 4 unique values in this city column, so we're going to end up with 4 unique values here. And then the columns, large and small, remain the same. Okay, so we're going to have, and then so there's no value for small and NYC. We only have NYC large 23. And there's no value for large with New York, right? So we got New York small 14, but we have nothing for New York large. Okay, and so we're going to get missing values here, NA and NA. Sometimes, indeed, you actually have different things. So maybe this isn't just a misspelling or something like that, but maybe it's actually a different city and you only have the large particle amount or something, and you don't have a measurement for the small. And maybe you don't want to put in NAs, but you want to put in some kind of different value. And so you could specify that. You can say, you know what, rather than an NA, put in a 0 instead. Okay. And so that's a possibility. And you can specify that using values underscore fill. Okay. And, you know, just for kind of teaching these slides, I've been putting all of the arguments on their own line. And I think that makes it a little bit easier as far as reading for teaching purposes. But of course, when you write your own thing, you don't have to put them on their own lines. Okay, so you can have everything in line. But just as far as, you know, teaching these slides, I think having them arguments on their own lines easy to read. Okay, so you can put in the fill value to 0, and that's good. All right, and then here's just another example, and I think you guys got a handle on this, but here, so I have all the city names spelled consistently: New York, New York, London, London, Beijing, Beijing. But here, as far as the size goes, we have an all caps large, and then we have small, large, small, large, small, large, okay? And so if I pivot wide this, what's gonna happen is it's gonna look at the unique values in the column size, and basically each unique value in the column size is gonna get its own column. And so the resulting table will have 3 rows, a row for New York, London, and Beijing, but it's going to have an additional column, okay? We're going to have a column for all caps large and a column for lowercase large, okay? Because it's viewing this all caps large as a unique value, okay? And we have little lowercase small, lowercase large, and these values reappear, but the resulting table, we got, you know, a column for each unique value. And so we end up getting this. And so we're going to end up having NAs for all caps large, because we don't have London all caps large or Beijing all caps large. And we end up getting an NA for lowercase large for New York. Okay, so it just populates the table as such. And so if you are going to, you know, scrape data from the internet, or, you know, or just somebody gives you a data file, but it's a little bit messy, it's very important that you clean and sanitize the entries in your column. So you might have to do some text processing to kind of make sure that people are spelling the city correctly, right? You know, when I asked people, like, what city are you living in? I had people write LA, Los Angeles, you know, LA area and things like that, Westwood and stuff. And you have to kind of go through and sanitize stuff. And that stuff is, it's tedious and it's not fun. And we'll cover regular expressions next week. But yeah. And chances are, if you take an internship somewhere, they're going to give you some boring, tedious job like cleaning up the data entries in something like that. And if you can find ways to automate and speed things up, you know, that's great. But a lot of times it's not easy. When you scan data, or if you scan papers, right? So like somebody might have taken old books and you scan them, and it's like so annoying. You'll have things like the number 13 gets interpreted as a B, or the letter B gets interpreted as a 13, or like H gets appears as I, and things like that. And it's just like, oh gosh, we got to clean this up. And because, you know, when you try to do stuff like this, it blows up. So, okay. So as you've noticed, pivot longer and pivot wider are inverse operations. So I think Angela kind of pointed this out. Indeed, here is my pollution table where all of the values are appear in this column amount, and we ran pivot wider so it spreads out across 2 columns. But this is just the inverse of doing pivot longer. Okay, so we took pollution, we did pivot wider, and we got this, and we said, oh, okay, this is tidy. But someone could take a look at this and say, oh no, I want to turn this back into this. I want my data gathered back into one column, and we can take this and pivot longer, and we get back our original data. Same exact thing for the cases table. Here, this was I said, we have our data spread out across 3 columns, and I want to pivot longer into this, okay? And we've done and we took these 3 columns and we gathered them into one, and that's called pivoting longer, okay? And the resulting table is indeed longer, okay? And then you can undo this operation, okay? The inverse of pivot longer is pivot wider, where you take this column counts and you spread the values out, okay? You pivot that data across multiple columns, okay? So pivot longer and pivot wider are inverse operations. And so depending on what you are trying to achieve, you might look at this and say, this is the format I want, or you might look at this and say, this is the format I want, okay? And, same here. In this case, you might want your data in this format. You might want to have the years in different columns, and you might want to say, because you can, if the years are spread out in this form, you might be able to do some kind of operation and say, what's the year over year difference between 2011 and 2012 and things like that, okay? Or, there's other functions that can be done, but this is at your disposal as far as kind of restructuring the data into a format that's useful for you. So it's always important to kind of think about where you're headed and what it is that you want to achieve, okay? Transposing is a little bit different. It's not quite the same as transposing. Transposing is taking data that looks like this and just kind of, switching the orientation. Whereas here, what we're doing is we're gathering values across multiple columns or spreading the values out across multiple columns. Okay, this is what we looked at today was a summary of pivoting, and you can read more on the kind of the documentation for each of these packages. Okay, so your best learning resource, I would say, is the documentation. I would say you should go to documentation first. So anytime you're trying to learn how to do something in R, I strongly recommend starting off with the official documentation. If you're still stuck after reading the official documentation, then you can go onto Google and type in whatever it is you're trying to do, and then space tutorial, right? So you can do like tidyr space tutorial or something like that, and you might find some examples here, but here, this is the pivoting vignette, and I think I covered most of this. There's a few more detailed examples that you can work through. There's another function that tidyr does, and it's called rectangling. It's a little bit of a strange thing. So if you go to the tidyr documentation, it says there's kind of 5 main categories, and we really only covered pivoting. And I would say this is when I use tidyr, this is like 90-something% of the use cases for tidyr. But rectangling is actually useful if you're dealing with data, especially from like JSON files and stuff like that. But then there's also other things you can do. And so rectangling is the idea of a lot of times or sometimes you might have data where the data, the values are lists contained inside of lists. You'll have like these nested lists. And so, for example, there's a data set called Game of Thrones characters. Okay, Game of Thrones characters. And I don't know if you watched the show at all, but inside the Game of Thrones characters data set, you'll have the name of a character like Theon Greyjoy. And one of the values, okay, some of the values themselves are lists, because the data set will say like Theon Greyjoy appeared in these seasons of the TV show. Okay, so there was a total of 8 seasons, and I think the data set only got updated through the 6th season, which was really which was the end of the good part of the show. Okay, but and so in Game of Thrones, some of the characters, get killed off, at the end of the 1st season or the 2nd season or in the middle of the 5th season or whatever it is, right? And so it'll say like this character appeared in 2 seasons of the TV show. Okay, this character appeared in 1 season of this TV show. This character appeared in 6 seasons of the TV show. And so, as far as the values in this column for TV series, it's going to be a series. It's they are you get kind of its own vector. Okay, so Theon Greyjoy appeared in, as far as this data set shows, says it appeared in seasons 1, 2, 3, 4, 5, and 6. Okay. And so you'll have these data sets where the values themselves are lists or vectors of an extra length. And so rectangling can help you work with data that looks like that to kind of turn it into a form that you want to work with. But a lot of times it requires you to think about what exactly you want to perform with the data, and that's going to guide what operation it is you choose as far as reshaping it. Okay, so if any of those things sound useful to you, I encourage you to check out the tidyr website and the documentation that goes along with it. I would say pivoting is probably the most important action of tidyr, and so that's why I covered that. But the other stuff is there as well, and so it's worth checking out. Okay, question: before doing anything, we need to decide to make it longer or wider, any generic operation. Well, before you do anything, you got to think about what it is that you actually want to do. And maybe your data is already in the form that you need to work with it. But in other cases, you might say like, okay, I actually need to reshape my data. I need to pivot it longer or wider. And it depends, everything depends on what your end goal is. And your end goal is basically, if you need to do some kind of operation, ideally you can do a vectorized operation where you can just do this column minus this column, or this column times this column, or something like that, as far as doing your calculations. And if all of your values are stored within one column, that's going to be a problem. And if you've got the same kind of value stored across, spread out across multiple columns, and you kind of want to combine them as well, that could be an issue as well. So, okay, let's go ahead and end here for today. And let me give you your last quiz answer. Last quiz answer is the letter A. A as in apple. A as in apple is the last quiz answer. Okay, that's it. Have a good weekend, you guys, and we'll see you guys on Monday. And I think some of you I'll also see. Well, I don't know if any of you I'll see for dinner, but yeah, have a good weekend, and we'll see you guys on Monday.
Thanks, Professor.
Thank you.